Yeah, hello everyone. We'll start within 2 to 3 minutes. Okay, please wait. Same DSS, sir?
Yes, sir.
Sir, you're ready, right, sir?
Yes, sir.
Yeah. Hello, welcome you back to the lecture 11, which is on power quality issues and analysis. And then the mitigation of how the power quality is improved also. Over to Dr. Sreenivasarao.
So, good morning to everyone. Am I audible?
You're audible, sir.
So today we'll discuss about the power quality problems that are arise in the distribution level. So first we'll start with the power quality problems. So next we'll start with we'll discuss about the power quality problems and their solutions. So there are different solutions are there, and so we will mainly focus on the distributed static synchronous compensator for three-phase three-wire and three-phase four-wire systems. So later on we will discuss about the simulation and so what are the precautions we need to take under the experimentation. Yeah. So you might have know that the power quality is normally deals with the deviations in the voltage and the currents from its ideal waveforms. So we expect that the waveforms are sinusoidal and free from harmonics, and also some other aspects of waveforms will be there. So there are different definitions for the power quality problems. So this one is defined by IEEE, right? So whereas other definition for this power quality is like this. Right? So power quality is the concept of powering and grounding sensitive equipment in a method that is suitable to the operation of the equipment. Okay. So main thing is that so here so it should not deviate the normal operation of the equipment. Similarly, electromagnetic compatibility is an ability of the equipment or the system to function satisfactorily in the electromagnetic environment. So without introducing electromagnetic disturbances to anything in the environment. So this one talks about the power quality, right? So whereas this one will talks about the electromagnetic interference thing, right? So there are several power quality problems will be there. So one is the transients. So transients are the unexpected variations in the voltage or the current waveforms, which are known as the transients. We have voltage transients are there and the current transients are there. Similarly, we have long duration voltage variations and the short duration voltage variations. So these long duration and short duration variations will be voltage sag or voltage swell or these things. So voltage sag means reduction in the uh, reduction in the small voltage deviation. For example, we assume that is 100% is the voltage magnitude. If it is reduced to 90%, so we have voltage sag of 10%. And if it is increased to 110%, so we can assume that the voltage swell of 10%. So depending on how much duration it will withstand, so based on that we have a short duration voltage variation and the long duration voltage variations. In case of short duration, so it is usually lasts for 2-3 cycles. So whereas for longer duration, so it may be persistent, it may be there for 1 minute or 20, 30 cycles likewise. Okay. So the main reason for this voltage sags or swells is the turning on some heavy loads like the capacitor, banks, or some inductors, or turning on a large motor. Right? So these will create some voltage sag in case of turning on a large motor. So that will create voltage sag. So whereas when you're turning on a large capacitor, so that may produce some voltage swell in the lines. Right. So next thing is the voltage imbalance or voltage unbalance. So voltage unbalance is the deviation in the magnitudes and phase angle difference. So as this unbalance may be of two types. So one is the magnitude unbalance and the phase angle unbalance, right? And the combination of these two, both magnitude and the phase angle unbalance. So you know that, right? In case of three phase, so we expect that the magnitudes are same. Like in this case, if there is unbalance will be there. So in that case, we expect that the magnitudes are different for different phases. Whereas phase angle imbalance, we normally expect that the phase angle is 120 degrees is maintained among the phases. But the point is here is that some due to some reasons, so we will not maintain this 120 degrees. And other unbalance, so we have both magnitude unbalance and the phase angle unbalance. So that consists of both things. So this is about the voltage imbalance or the unbalance. So next one is the waveform distortions. So waveform distortions. So waveform distortions are these are the main ones. So we need to focus. The first one is the DC offset. So DC offset means if you have an AC waveform is there, so the DC voltage will be induced on this AC waveform, something like this. Some DC offset is there, and if you are adding these two signals, the waveforms will be slightly. It will be like this. Yeah. So this DC offset, that means having some DC voltage in an AC, it means superimposing a DC waveform in a AC waveform. Right. So this is extremely dangerous, so especially when you have a transformers are present in the system. So this DC will saturate the transformer core and it will increase the magnetizing current. And if the magnetizing current increases, that leads to the losses in the transformer. To avoid the losses, so what we have to do that means we need to increase the size of the transformer. Okay. So that means we need to avoid this DC offset. So that means having a DC value in a AC waveform. So next is the harmonics. So this is another important thing. So you know that, right? Harmonics is the integer multiples of the fundamental frequency, so that will exist in the waveform. So any periodic waveform that we can decompose into one fundamental waveform and some set of harmonics. Right. So these harmonics are broadly classified into several ways. So one is the characteristic harmonics and the non-characteristic harmonics. So these characteristic harmonics are the, so that consists of certain magnitude or certain harmonic number. So we can define. For example, if you consider the three-phase rectifier circuit, let us assume it's feeding some R load or something, right? And you assume that the load current is constant on the DC side, so that will produce a waveform something like this. This is the input current waveform of three-phase rectifier. So if you decompose this into Fourier components, you will usually get some harmonics like fifth order harmonics, 7th, 11th, 13th. So that means the harmonic order will be 6k plus or minus 1 on the AC current side. Similarly, on the DC side, we have 6k order harmonic, like 6th order harmonic, 12th, 18th order harmonic on the DC side output voltage. Right. So here these are characteristic harmonics, irrespective of the load conditions or irrespective of the firing angle. So we always expect this kind of harmonics in the three-phase rectifier circuit. Yeah. So that's why it is known as the characteristic harmonics. Similarly, for in case of 12 pass converter, so that means harmonic order will be 12k plus or minus 1. So that means we have harmonics of 11, 13, and 23, 25, and so on. Right. So this is known as the characteristic harmonics. So that means we can easily predict the order of the harmonics. We can easily predict the order of harmonics. So whereas non-characteristic harmonics, like we cannot predict that one, so they will randomly generate. For example, if you are using a PWM output voltage waveform, so in that case, some harmonics are characteristic harmonics and some are non-characteristic harmonics. We cannot predict the exact spectrum. For example, whether 20th order harmonic is present or not, that we cannot predict. Right? That all depends on the what control you are using or what current it is flowing. So that all depends here. Right? So these are known as the non-characteristic harmonics. So there is another group of harmonics, right? So there is another group of harmonics which are known as the which are known as interharmonics. Interharmonics, right? So with these interharmonics are not an integer multiples of the fundamental waveform. Let us assume if you have 50 Hz waveform is fundamental, right? If you have 250 Hz harmonic, so that means you can easily say it is a fifth order harmonic. So whereas if you have 270 Hz harmonic, so which is not exactly integer multiple, right? It may be around 5.4th order harmonic, right? It's a 5.4th order harmonic, so which is not in integer multiples. So these known as the interharmonics. So these are known as the interharmonics, which are non-characteristic harmonics, non-integer multiples of harmonics. Okay. So the main sources for the interharmonics is the one is the AC voltage regulators, AC voltage regulators, so which are using some integer integral cycle control. So that means integral cycle control. If you are using an AC voltage regulator, so in few cycles we will turn on the all switches, that both switches, and the remaining few cycles will turn off the switches. So that kind of control that produce the interharmonic. Similarly, cycloconverters. So that also produce this kind of interharmonics. And there is another group of harmonics, so which is known as subharmonics. So this subharmonics, for example, you have a 50 Hz system is there, right? So if you have a harmonic of 40 Hz, right? So this is known as 40 Hz, 30 Hz. That means less than the fundamental, so which is known as the subharmonics, right? So which is known as the subharmonics. Right. So we have characteristic harmonics, non-characteristic harmonics. Similarly, we have interharmonics and the subharmonics. Interharmonics is not the integer multiples of the fundamental frequency, whereas subharmonics, right? So here the harmonic order is less than 1, right? Like 0.8 order harmonics. For example, the 16.67 harmonic, so that is usually produced from the traction, electric traction supply. Right. So notching in the waveform. So notching is the sudden reduction in the magnitude. For example, some voltage waveform is something like this, right? So notching means here you have some dip in the waveform, right? If it is at the peak value, the dip may be something like this. But whereas if it is at the near to the zero, so in that case, there is a chance that so that will touch the zero. But for example, it is at the beginning, right? So there is a chance that it will touch the zero. The dip may chance that it will touch the zero value. So these are known as notching in the waveform. So one of the main source for notching is that let us assume that in case of thyristors, there is a chance that the two during commutation, so there is a chance that two devices will be simultaneously turned on. That may lead to the short circuit of two phases for a brief period of time. So under that case, right. So there is we can expect that there is slight reduction in the output voltage or this voltage waveform. So this is notching. So why we need to avoid this notching is that, for example, you are using some firing angle control. So normally firing angle control is synchronized with this 0 points of the supply voltage, right? If you have a notch here, for example, if you have notch something like this, right? So this notch is treated as a zero crossing. Right? So therefore, we need to avoid this notching. Right? So this will act as a zero crossing, and the new firing angle may be measured from this point onwards. So that gives you the errors in the control. And another thing is the noise. So noise is the imposition of high frequency component in the waveform, that is noise. So this noise will introduce electromagnetic interference with the surrounding communication circuits or the surrounding control circuits. So next one is the voltage fluctuations. So voltage fluctuations will be the something like this. So if you have arc furnace loads or something like, the voltage fluctuations will be like this. Right? So that means a continuous deviation in the magnitudes. So that is known as the voltage fluctuations. So that is this is also known as the flicker. Right? So voltage flicker. So due to this flicker, so we can perceive some disturbances, especially so when it is attached to some fans or some fan loads or some light loads. So one of the main sources for this voltage flicker is the arc furnace loads. Arc furnace loads. So one of the main source that right, during the welding or arc furnacing applications, we have some different sequences will be there. In one sequence, we will generate the arc, and another sequence will short circuit the arc terminals by using some metallic plates. Right. So during that, there is chance that so this will voltage fluctuations will occur. So next thing is the power frequency variations, so that we know that the frequency is 50 Hz or 60 Hz. If there is a slight variations in the frequency, especially when you're increasing when you're increasing some sudden change in the active power command or something, right? So this power frequency variations will occur. So nowadays, due to this microgrid, so we can expect that a lot of power frequency variations. Right. So normally this frequency is related to the active power, and this voltage is related to the reactive power. So this is normal case. In case of short circuit ratio is very high. In case of short circuit ratio is very less. In that case, the rules will be changed. Yeah. So now we have this microgrid and all. So therefore, we can expect this. We'll inject a lot of active power into the microgrid, and we will draw more active power from the microgrid. So therefore, we expect that this frequency variations is very common nowadays. So these are the different power quality problems, right? So one of the main sources for power quality is that lighting and the natural phenomena is a failure of equipment like transformers, cables, and energization of large capacitor banks and transformers, switching and starting of large loads such as capacitors and motors. Right. So another thing is that so operation of reactive, non-linear, and unbalanced loads. So these will cause the different power quality problems. Some of the things are natural. For example, this one is lighting, and all these things are natural things, but we cannot stop that. Some these things also we cannot stop, but we can have focus on this one, like this reactive power, not large reactive loads, non-linear loads, and unbalanced loads. So next thing is that reactive and nonlinear and unbalanced loads. Right, we have two different systems is there. One is the three-phase three-wire and three-phase four-wire. So three-phase three-wire means there will be three phases and three conductors. There is no neutral here. Whereas in three-phase four-wire, so we have neutral will be there. So neutral, in case of three-phase four-wire, so the neutral will be either grounded, right? Neutral is grounded, or this neutral is used as a return path. Neutral is used as a return path. So in that case, it is known as three-phase four-wire. In case of three-phase four-wire, so there is no neutral at all. It is neither grounded or nor accessed. Okay. So in case of three-phase three-wire, so some of the commonly problems is that so harmonic current burden, so reactive power burden. And in case of three-phase four-wire, so we have harmonic current burden, reactive burden. In addition to that, so we have unbalance in the load currents, so that cause the high neutral currents. So reactive power burden, so it may be caused due to the rectifiers, motors, transformers, or choke inductors. And in case of harmonic distortions, depending on what kind of voltage or what kind of power level you are dealing with. So based on that, so we have the first thing is the adjustable speed drives, so that is motor drive. And another one is the HVDC converters, traction applications, arc furnaces, static wear compensators. These are one of the sources for the harmonics on the distribution level. This is on the transmission level. Right? So low voltage power electronic devices like uncontrolled rectifiers, controlled rectifiers, AC voltage regulators, inverters, cycloconverters. Right? So these are the low voltage sources for the harmonics. Conventional sources like electric machines, transformers, in the stroke inductors, this also produce some kind of harmonics. And we have some modern equipment like the personal computers, laptop chargers, or the photocopiers, air conditioned televisions, UPS, microwave, fluorescents, and electric vehicle battery chargers. All these usually produce some kind of harmonics into the system. Right. So what kind of loads? So which are more common here? Mostly that for this rectifier circuits are used for AC to DC conversion for any sort of applications, like it is a motor drive or handheld tool or any air conditioner or anything, right? So first step is that so we'll convert this AC into DC. Right? So in early days, we normally use different types of rectifier circuit, like single phase rectifier or the three phase rectifier. Right. This is the first step, right? So first thing is that AC we need to convert into DC. So most common loads, so that we will see is this kind of loads in this controlled rectifiers and uncontrolled rectifiers. Right. So this is uncontrolled rectifier and this is uncontrolled rectifier, which are most common. It may be single phase or it may be three phase, depending on what power level you're dealing with. So this is when you are open any power circuits. So this is the first circuit you will see. One diode bridge rectifier followed by a capacitor. One diode bridge rectifier, so followed by a rectifier, followed by capacitor. So that is the starting point of any power converter. Right. After that only you will see the other converters, how the DC is utilized for your application. So here there are drawbacks with this type of converters. So these converters, so one drawback is that first thing is that harmonic currents, and another drawback is the reactive power. So first thing, if you see that uncontrolled rectifier with R load, and this is the waveform that is obtained on the three-phase input side, and its corresponding THD is somewhere around 27.4% THD. Right. So this is with R load. Sim, this is with RL load. You can see that this is RL load. The load current is constant, so that's why we have straight line here, and the THD is around 28.7 percentage. Right. This is usually motor kind of load if you are connecting a DC motor on the other side. So whereas this RC load, so which is more common in a power supplies. So if you see that the THD is around, it is, you can increase the THD here. The THD is around 42.2 supply, 42.2 percentage. So this kind of loads are more common. So this RC loads, all the power supplies, so where that require AC to DC conversion, so we can normally treat or we can model as a RC load. So you can also see that the waveform is distorted. So that's why we have the higher value of THD. So when you're operating at some other range, even the THD will be crosses 70%, 80%, something like that. And we can see that the huge value of the third order harmonics, fifth and seventh order harmonics, a large spike in these harmonics. So these are the problems with these conventional rectifier circuits. Of course, nowadays we have these active rectifiers will be there, active rectifiers, right? And also we have this power factor correction rectifiers or active rectifiers or the improved power quality converters, improved power quality converters. So these things are now we are replacing with these conventional rectifiers. So active rectifiers or power factor correction rectifiers or improved power quality rectifiers. So the difference is that in case of rectifiers, so these are based on the diodes or thyristors, right? If you have active rectifiers or active front-end converters, where they do the job of AC to DC conversion, they're not based on these diodes or thyristors. They're based on MOSFETs or IGBTs. MOSFETs or IGBTs are self-commutated devices, and there are certain advantages with them. One is that so it will make all the source current sinusoidal, right? So no control is required. It will make the source current sinusoidal. So that source currents are sinusoidal, and also the source currents and source voltage are in phase. That means the power factor is unity. So that's why it is known as unity power factor converters. It will make the source current sinusoidal, and another thing is the power, it will make the power factor unity. So another interesting thing is that it will also regulate the DC voltage, right? So in case of this conventional converters, we cannot regulate the DC voltage, right? For example, thyristor converters, the regulation is not proper, right? So here it will also regulate the DC. For example, you want to fix the voltage at 400 volts. That 400 volts can be possible. And another thing is that these are bidirectional. So these active rectifiers are bidirectional. So that means it will draw the sinusoidal current from the source, and the source current and source voltage both are in phase. That leads to the unity power factor, and we can regulate the DC voltage, or else we can maintain the DC voltage at fixed value or variable value depending on your application. And it is bidirectional, so that means this we can regenerate it. That means the power flow is from the DC side to AC side. Okay. So this kind of merits are used, these kind of things are possible on these active rectifiers. So now all these circuits, wherever we have this AC to DC conversion, early days we are using this diodes or thyristors, single phase or three phase. So now we are replacing with these active rectifiers or active front-end converters. So that means the load itself producing some harmonics, and that itself the converter itself eliminating that harmonics as well. Okay. So in that case, if you are using every 100% power converters, so that rely on this active rectifiers, under this case, the DStatCom or this power quality solution power quality problems will not arise. So now we talk about these things, harmonics, effects of harmonics. So one is it will interfere with communication lines, electric equipments, malfunction of some solid state devices, and damage to the capacitors, because the harmonics, it will create resonance with the capacitors, and that capacitors, the quality factor, if the quality factor is very high, the voltage across the capacitor, which is equal to the quality factor times the uh, operating voltage. So that if I let us assume that if you are using 11 kV system, and the quality factor is somewhere around 5 or something, right? Under this case, under if it is resonant at some particular harmonics, the voltage across the capacitor will be quality factor times the operating voltage. So that means it is very high. Some malfunction of utility meter. Some utility meters may show higher readings that may lost to the consumers or that may lost to the power utility. So resonance phenomena as well as we discussed. So failure of sophisticated electronic equipment. The heat generated due to the harmonics are very high. So maybe it leads to the early failure of the electronic equipment. So flickering of the lights, as we discussed, if there is a fluctuations in the voltage waveform that leads to the flickering, and sometimes here operating it for a longer duration that may our eye may perceive these disturbances, and also it will damage the lights, LED lights or very quickly. There are several solutions for these power quality problems. So one common one is the solutions are based on the divided into several ways. So one is the reactive power compensation, harmonic elimination, and the neutral current compensation. In early days, so we have different solutions for different things. For example, if you have reactive power compensation, they may use these condensers or these static wear compensators or this thyristor controlled capacitors or the thyristor controlled reactors. Right. So these things they used early days, and also they used the StatCom in case of distribution level to compensate the reactive power. For harmonic elimination, so we have some solutions like active power filters or passive power filters, active power filters, and combining these two, so which is known as the hybrid power filters. These are the solutions that used. And in case of neutral current compensation, so they normally use the passive power filters or these transformers like zigzag transformers or some transformer with converters. They combine these things to compensate the neutral current. So by combining all these things, so we have one application or one devices which is known as the custom power devices. Right. So these custom power devices, so that deals with all power quality problems that arise in the voltage and the current waveform. So these custom power devices similar to the FACTS. So FACTS are used to improve the power flow control in case of transmission line. So whereas these custom power devices that are used to improve the power quality in the distribution lines. Okay. The power circuits are same. Only thing is that their control is different. Right. All the power circuits are same, but their control objectives are different. So come to this passive power filters. So this passive power filters, it may be single tune filter or the double tune filter or this high pass filters, so which are commonly used around 20 years ago. So we can observe some drawbacks with the this passive power filters. So one drawback is that they're heavy because it consists of inductor and capacitors and also produce a lot of losses, and their filtering is not appropriate. For example, you're tuning this fifth order harmonics. For this one, it will only tune the fifth order harmonics, whereas this one double tune filter, so we can compensate maybe fifth and seventh order harmonics. So for this one, it may be for higher order harmonics like uh, more than 11 and 13. So usually it is design is something like that. If you have harmonic order of fifth and seventh order harmonics, right, and also 11th and 13th order harmonics, it will be like this. So maybe we can install one fifth order harmonic here for a single tune filter fifth order harmonic. This is also another single tune filter for the seventh order harmonic. Maybe the double tune filter is for the 11th and 13th order harmonic. And beyond this 13th order harmonic, after that, what we will expect that 17th and 18th order harmonic. So this is for 17th and 17th order harmonics onwards. So this much setup you need to have to compensate the harmonics. And another going to all these things, we cannot fully compensate the harmonics. And another thing is that, so you know that, right? So whenever some due to aging, the capacitors will deviate from its operating means whatever the harmonic frequencies that we are tuned, right? So it will be cause some deviation. So that means earlier it is tuned to the fifth order harmonics. So due to aging, that resonant frequency is changed. Let us assume it is fifth order harmonic, which is due to the aging or the due to the deviations in these values. So that may find some new, the resonance may occur at the new frequency. Right? It may be some 5.5 or fifth order harmonic or something like that. If you see this spectrum, like this is the curve, impedance curve between the frequency and the magnitude of the jet, right? It may be like this. So due to aging, so this middle point, it will occur at some point. So it will be deviated and you will get the new frequency. That is one of the drawback. So therefore, what they normally do is that, so when they are installing this power filter, so instead of perfectly tuning at fifth order harmonics, they will normally use to tune at the 4.7th order harmonic or something like that. Right. So due to aging, what happens is that, so it will slightly increase, maybe after 1 year or 2 years. So this value will be slightly increased. Right. After 2 years or 3 years, so this becomes fifth order harmonic. After another 3-4 years, so it may be become 5.3rd order harmonic. Right. That means we can successfully operate this one in this range. This range. All right. So if the installation itself you are operating at the fifth order harmonic, what happens is that due to 5 years or 6 years, right? So this may deviate. You may get the 5.6th order harmonic or higher than that. So in that case, so your operation range will be changes. It will be operate in this region. Understood. So instead of perfectly tuned at some particular frequency, so they normally slightly reduce that frequency so that we can increase the operating characteristics. So the drawback is that, so resonance, so unwanted frequencies that also cause some resonance, and also the whenever there is a change in the loads, so there are always deviation in the resonant frequencies. Right? So there are limitations of these passive filters. So one is that they tune to the tune frequency, right? The filters can be easily switched on and turn off, right? So therefore stepless control is not possible. And the source impedance, so one of the main things. So here for obtaining the resonance, so you must know the exact value of the source impedance. The source impedance is always changing whenever some new transformer installed or something is installed, right? The source impedance is always changing. So therefore the source impedance is changing, that also deviate the resonant frequencies. Right. So due to aging, deterioration, temperature changes may also affect their tolerances. Right? Single tuned and double tuned filters are not possible to employ for certain applications like cycloconverters, right? Whereas some power system harmonic interharmonics are there. So outage of parallel branch can totally alter the resonant frequency, resulting in a overstressed filter component and increased harmonic distortion. For example, outage of this branch, right? So that may increase the burden on the high pass damped filter. Right? So that also we need to take in. So therefore, so we have this power electronic based solutions, so which are known as the custom power devices. So this custom power devices, it's a family of several compensators like FACTs. So one is the DStatCom. This is distribution static synchronous compensator. Another one is the dynamic voltage registrator, and this is UPQC, Unified Power Quality Conditioner. So this usually deals with the current related power quality issues, and this deals with the voltage related power quality issues. And whereas this one UPQC, so which is deals with the both voltage and power quality, both voltage and current power quality issues. So this is similar to the StatCom, right? In case of in case of FACTs, so this is similar to the SSC, and whereas this one similar to the UPFC, Unified Power Quality Condition, Unified Power Flow Conditioner, right? The circuit wise is same. DStatCom and StatCom, DVR and SSC, UPQs and UPFC, circuit wise same, but their objectives and their control and their placement of at what it's connected. So all things are changed. The power circuit but remains same. So among all these things, this DStatCom is most popular because if you the good thing is that, right, if you compensate the current related harmonics, so automatically we can compensate the voltage related harmonics. Most of the voltage related harmonics which are erased from the current related harmonics. If you have harmonic currents, right, so that harmonic currents due to the resistance losses, IR losses or IL losses, so that also lead to the voltage harmonics. That means if you tackle the current related harmonics, right, so mostly we can tackle the voltage related harmonics itself. And another thing is that voltage sags and voltage cells, so that also can be compensated by using this D-statcom by properly injecting the reactive power. By injecting reactive power also, so we can control the voltage magnitudes, right? Another thing is that the frequency fluctuations are there, right? So frequency fluctuations can also be done or can also be controlled by controlling the active or injecting some active power or injecting some drawing some reactive power from the source. So that also can be possible with D-statcom, so by suitably connecting a energy storage system, right? Suitably connecting a energy storage system. So therefore, this D-statcom is more popular. So that means with D-statcom, you can control the harmonics, current related harmonics. You can control the, or you can compensate the current related harmonics. You can compensate the reactive power. So it will reduce the reactive power burden, right? And also we can control the voltage magnitude at a particular bus, voltage magnitude at a particular bus by properly injecting the reactive power. And another thing is that we can control the unbalanced loads. So load balance is possible. Load balance is possible. So by doing all these things, whatever the problems that are there in the voltage, right? So that can be minimized, right? So that can be minimized. And also if your frequency fluctuations will be there, so there is another one. So we can also include a energy storage element in this D-statcom circuits. So now that becomes a E-statcom. So each statcom, so that is energy statcom, so that will act as a both, it will inject both active and reactive power into the system, right? So this way we can control the frequency component as well. So D-statcoms, so it will compensate the poor and load power factor such that the current drawn from the source has a unity power factor. It will suppress the harmonics in loads so that the current drawn from the source is sinusoidal. Voltage regulation for the loads such that cause fluctuations in the supply voltage, right? So cancellation of effect of unbalanced loads so that the current drawn from the source is sinusoidal, right? So these are the main objectives of the D-statcom. You can see how exactly it will work. So you have source is there. This source may be a medium voltage source. It may be 415 volts, somewhere between 415 volts to 11 kV, right? And we have all these loads are there, some different types of loads. So we all model this as some three-phase, three-by reactive and non-linear loads. Here some linear loads will be there, reactive loads will be all these loads. So this lumped as a one load, right? And we have this one is the D-statcom, right? So this is D-statcom, and this D-statcom is connected through this one. So these are known as the coupling inductors. Coupling inductors. These are known as the coupling inductor, and this is the point where it is connected. So this is known as the PCC, point of common coupling. So this is point of common coupling. So we have some optional inductors on this side. We have some optional inductors here. Right. So this inductors is to suppress the harmonics. This is optional. Similarly, we have some inductors will be present. It is not shown here. Some inductance will be present, or this one is source impedance. Source impedance. So this one is to this LAC. These inductors are to suppress the harmonics on the load side, and this one is the coupling inductor. This is coupling inductor. Right. So normally, so depending on the application, for example, 11 kV applications, we normally have some transformer will be there. Right? So we normally have some transformer will be there from to step down. It may be for 11 kV. It's 11 kV system, right? We need to design this D-statcom for 11 kV. So that kind of maybe it is costly. So therefore, we normally have 11 kV by some 415 volts, some 3.3 kV transformer will be there. Right? So from the transformer secondary terminals, so we can actually connect the D-statcom. So as we discussed, or if you see this one, right? So these two are parallel, right? So these two are parallel. So therefore, as we discussed in one of the class, so if you want to connect two parallel sources in two voltage sources in parallel, so their instantaneous voltage supposed to match, right? Their instantaneous voltage supposed to match. So here also the difference in this grid voltages and this inverter voltages, so this will act as a buffer, right? So this difference is x, or difference is like this. If you apply some KVL, so this grid voltage is equal to this coupling inductor voltage plus inverter voltage. Right. So on the other side, so here just only one capacitor. So here by this STATCOM, we are not injecting any active power, right? We are not injecting any active power. So we are just injecting some reactive power only. Okay. So we are injecting some reactive power only, but in the opposite direction. But truly we are not acting, truly we are not inserting any real power to this load side or to this side. Right. So that's why we have some small energy storage system is enough, so that will act as a buffer. But the point is that so we need to maintain voltage across this capacitor. We need to maintain voltage across this capacitor, or we need to regulate this voltage across this capacitor. So how to regulate that? So we'll discuss in shortly. Clear? The operation is very simple. So here, so this one is the source voltage here, right? And this one is the load currents. So here we want to make the source voltages or source current to sinusoidal, right? We want to make the source current to sinusoidal, this currents to sinusoidal, right? And these are the harmonic currents on the other side. So what we can do is that, so here we will control this D-STATCOM such that, or we'll control the current inside this D-STATCOM or inside this inverter such that, so here whatever this one, right? So this one is the nonlinear load, or right? So this is the closest approximation of a this waveform. So the different current, or the difference current between this closest approximation and this load current waveform, that must be injected, or that must be drawn from the D-STATCOM, but in the opposite direction, right? So that the source current will become sinusoidal, right? So from the source point of view, this will act as one load, and this is acts as another load, right? But thing is that, so if you are adding this current and this current, or this current and this current, you are supposed to get a sinusoidal currents on the source side. So here whatever the current here, right, the remaining current is the harmonic. This is load current, right? If you want to make it sinusoidal, the sinusoidal current minus this load current, that gives you the harmonic current. We are injecting, or we are drawing the harmonic current from the STATCOM, right? So here, if we add this one, or if we apply some KCL here at this one, right? So this current is equal to, so this current plus this current. Or in other words, if we add these two waveforms, you will get the source current waveform. So meaning is that, so somehow we need to control this D-STATCOM such that whatever the harmonics that are produced by the load current, so that's supposed to be compensated. In other words, we need to inject a current into the grid such that the harmonics currents on the load side is cancelled out. Right. So from the source point of view, so this entire thing acts as a just linear load. This entire thing acts as a linear load. So therefore, both source voltage and source current, so both are in phase, and also the source current is sinusoidal. Meaning is that, so we compensated the reactive power, and also we compensated the harmonics. Right. So this is how a D-STATCOM will work. So interesting thing is that, so we need to maintain a voltage across the DC capacitor, or this DC link. So to maintain this one, so actually we will not draw any active power, right? So to compensate this one, so we will draw some small amount of active power from this, right? We will draw some small amount of active power from this source, so that it can compensate the or it will maintain the voltage across this capacitor. So how exactly we'll do that? So we'll discuss shortly. Right. The same thing if you are adding something like some battery or something like this. It may be battery or some PV. So this thing will become a E-STATCOM. So with this, you can also inject the active power, right? You can also inject the active power, right? For example, you have some voltage fluctuations here. If you want to inject some, we know we calculate the depending on fluctuations. So what kind of active power we want to inject? So that active power, so we can inject from the from the E-STATCOM to the source. That also possible. For example, to charge this one, so we can also charge this DC source with this, right? So in case of this load is absent, if this load is absent, sometimes we can also feed this load. Sometimes we can also feed this load. So in this case, it will act as a inverter, or known as a grid forming inverter. So all these things are possible. So when you are connecting a STATCOM, so with some load. So this will act as a battery energy storage system, right? It will act as a battery energy storage system. It will act as a D-STATCOM, right? It will act as a D-STATCOM. If at all you want to integrate some PV, right? If you want to integrate some PV, so this is also possible to integrate some PV. So under the absence of the main grid, or it will also act as a standalone mode. So we can operate this as a grid forming inverter, right? So this itself will form the grid and it will feed the load. So these are the benefits so that we can obtain by adding a DC source to the STATCOM. Right? The control of this D-STATCOM, right? And another thing is that so this D-STATCOM and this active power filters are we can both or this both terminology can be used interchanged. So this active power filter and the D-STATCOM, the control objectives are same. Sometimes we use this, or sometimes we call it as a D-STATCOM, or sometimes we call it as a active power filter. Right? But both are same only, right? In general, if it is active power filter, it depends on earlier days. For example, if an industry is there, right? Industry is there, and this industry is fed from some other power supply. Right? So if you connect a if you connect some D-STATCOMs, you have it's for the same thing. You have another industry is there, right? Okay. If they are connecting their individual filters, right? Right. They're connecting their individual filters for harmonic compensation. So which is known as active power filter, right? If they are active power filter, if the power supply itself have their own thing, right? Own setup for the compensation of reactive power. So under this case, maybe they will call it as a D-STATCOM. Right? If the load that we are compensating at the same vicinity, right? So that is usually known as active power filter. If it is at the directly installed at the distribution network itself or distribution station itself, that is usually known as D-STATCOM. But it doesn't matter, right? Whether it is compensating their own loads or their combined loads, but the control is remains same only. So that's why, so this D-STATCOM and active power filters, these two words can be used interchangeably. Right? So this is the overall setup here. So we have some applications like some speed control, motor drive is there, some load is there, or something like that, right? And we have supply here, and this we need to sense the voltages here, and we have some protection circuit here, and we need to sense the load currents. So we normally have some sensing or some boost inductor or the coupling inductor here, and we have this power converter, right? So this is all the control of the STATCOM. The first thing is that, so if you want to inject or if you want to operate the power converter, and if you want to inject what kind of harmonics into the system, so first thing is that, so we need to observe or we need to calculate so what kind of harmonics that are present in the load side, right? So based on that we can do that, right? So next thing is that, so DC voltage controller, so that means your objective is to maintain the DC voltage across this capacitor. That also we need to do. The main thing of this D-STATCOM is that, so you can see here, right? The first thing is that the predicting the what harmonics inside the load waveform, predicting the harmonic inside the waveform, load waveform, and predicting the shape of the source current. You know this current, right? You know this one. For example, this is not connected, right? This is not connected. Both source current and the load current both are same, right? If you are connecting this one, so we need to control this D-STATCOM such that we need to make this source current sinusoidal, right? So that means we need to predict the, or we need to calculate, or we need to estimate the source currents waveform, or we need to expect or expected source current waveforms that we need to predict. If you want to predict that, so you need to measure this load currents, and from that you need to analyze this, and we can predict the approximate equal or approximate or the nearest waveform which is close to a which is nearest sinusoidal waveform for the source current. Understood? So that means reference current generation is important, right? So that means the reference current generation for this D-STATCOM important, right? So this, as we discussed, this is operating as a current control mode. So that means we need to obtain the reference current for this. So there are numerous methods are there, like Fourier-based detection methods, power balance theory, instantaneous reactive power theory, synchronous reference frame theory, symmetrical component-based theory, or some Adeline-based control, that is using fuzzy logic, or some artificial intelligence methods, or this model predictive control methods. So these things are commonly used to extract the extraction of load current harmonics and reactive power from the source. That means we need to extract the harmonic load current harmonics and the reactive currents in the load currents. Okay. So most commonly used techniques are this instantaneous reactive power theory and also the synchronous reference frame based theories, so which are commonly used. So one method, so which is more common thing, is that instantaneous reactive power theory. Right? So in case of instantaneous reactive power theory, so this is proposed by Akagi in around 25 years ago, which is known as IRP theory or the PQ theory, which is most popularly used. The first step is this theory is that, so we'll transform this in this load currents and the source currents into ABC reference load, PCC voltages and the load currents into ABC reference frame. So these are the voltages on the source side, and these are the load currents. So the thing is that we will transform this into alpha beta reference frame, or by using this Clark transformation, it's where you're preferring this one. So next we will find out the powers in alpha beta reference frame. So this is active power and this is reactive power, and this is the zero sequence power or the zero power, which is P0 and I0. Under balanced conditions, this value will be 0. So if you observe this power waveforms, right? So if you observe this waveforms especially, so this waveform consists of, this P consists of two components. One is PDC and PAC component. Similarly, this Q consists of QDC and QAC component. So, but what you observe that, if you see the spectrum, so you have one DC component and one AC component in these two. Right. So here, if you more closely, this one, right? So this one, right? So this one is responsible for the fundamental component. What you observed that, so this one is responsible for the fundamental component. So whereas this AC side power or AC power, so which is responsible for the harmonics. So that means, so here normally if it is both are sinusoidal, both voltage and currents are sinusoidal, we can expect a power line, something like it's some straight line, right? If there is no harmonics, or it is not drawing any harmonics, you can expect something like this. If it is harmonics are present, the power line, it will be something like this. So that means it consists of both AC component and as well as DC component. So this DC component inside this one, so which is responsible for the fundamental. So remaining AC components here, this high frequency AC component here, so which is responsible, which is due to the harmonics. Similarly for Q as well. Similarly for Q, this is O1, right? So here, so this one is P, right? It consists of both AC and DC component, and this is the DC component, so which is due to the fundamental, and we have these ripples or this frequency components or AC component, so which are due to the harmonics. Similarly, on the reactive power, so we have Q, that is AC component and the DC component. So one is due to the, this one is due to the fundamental, and this one, this oscillations or this AC component, so which is due to the harmonics. Right. So somehow, so that means we have identified this. So we identified that it consists of both components, AC component, DC component. So here, depending on that, so we can select the objectives. If you want to eliminate this, or somehow if you eliminate this AC component, right? So that means from the source point of view, so it will act as a linear loop. And another thing is that, so this is reactive component or the reactive power. What we can do is that we need to, no need to separate AC component or DC component, right? Our objective is we can completely eliminate this component. We can completely eliminate this component. Right? So for that, you need to see here. So this, it consists of P and Q. So both P AC component and P DC component here. Similarly, this is Q DC and it is Q AC component here. But what we require on the source side, so this source side is supposed to be P DC component, and ideally we need to make Q as 0. Understood? Right? So ideally this is our requirement, right? If you are doing so, we eliminate the reactive power and also will make the source current sinusoidal, and we will eliminate the harmonics. But in the load side, it consists of both kind of powers, AC power and as DC power. So accordingly, so we can choose. That means here this P is supposed to be, if you want to cancel this, so this P is supposed to be, so this minus P AC only, right? If you are adding these two, you will get this P dash only, right? And similarly, this Q is supposed to be minus Q. In other words, it is minus of Q dash or QAC or QDC. So your control of this one or this StatCom is such a way that it's supposed to produce these powers, right? So that you will get only fundamental power on the grid side, and you can make the reactive power 0. So if you are adding these two from the grid point of view, these two will act as loads. So these two are loads. If you add this one, if you add P plus P minus, if you add this one, right, you will get P AC only. If you are adding these two, you will get 0. Right? So this is how we can control the D-STATCOM current. So now these are the powers that we need to compensate. So these are the powers we need to compensate, or based on these powers, so we can control the inverter. Right. So this matrix, this power matrix, whatever this one, right? So this we can put in a matrix form like this. So this is the matrix here, and this is the compensating powers so that we want to do. So these are the compensating powers so that we want to eliminate. Right? So these are the powers that we want to eliminate, and these are the reference currents for the D-STATCOM. These are the reference for the D-STATCOM. So this minus PC, so as we discussed, we want to compensate only the harmonic part, right? So that's why we have, if we subtract this one, right, you will get only the AC power, and this minus Q can compensate the reactive power. So whereas this loss component, so this loss component, right? So this is important. This is due to the so as we discussed, we have one capacitor on the inverter side. So we need to regulate this capacitor voltage. So we need to regulate this capacitor voltage. So we need to regulate this capacitor voltage. So here there is no provision to, or we are not allowing any real power drawing from the this grid to this from grid to the inverter side, right? Theoretically, but the thing is that, so here we need to maintain this one because it will act as a boost type, right? For example, this 415 volts are there, right? And here it's supposed to maintain some voltage here. If it is not, let us assume that you're not giving any firing pulses here, right? If you're not giving any firing pulses to this converter, so what happens is that it will simply act as a, see, let us assume this is absent, it's not present, and you're not giving any firing pulses for this. Okay. So that means, so this will act as a three-phase diode bridge rectifier. So this will act as a three-phase diode bridge rectifiers, and this capacitor voltage will be something like this. You will get an output voltage something like this. If your capacitor is large, it will make this voltage something. So what is the minimum voltage? It is 3 Vm by pi. That means by default you are getting a voltage 3 Vm by pi here. Right. So if you make these devices in forward bias, right? So you must have voltage higher than this, right? So that means your VDC, you need to select something like this. So you must have a VDC value somewhere here so that this IGBT will become forward biased. Okay. So that means you need to select a voltage. It is 3 Vm by pi. You need to select a voltage that can be more than the diode bridge rectifier voltage. Theoretically, so if you have 415 volts is there, right? Or 415 or 450 volts, must the DC link voltage must be 1.6
Circuit need के लिए
volt.
संबंध रखता है circuit 300 nodes.
So this DC link voltage is usually 1.6 more than that, so that the device will be forward biased. Understood? So we need to regulate this DC voltage. If you are not regulated, right, what happens is that it consists of all losses. The converter consists of several losses and all, right? And there is no provision for the real power supply. So that means this is only having the capacitor, right? So whatever this energy stored, right, that is used to compensate the losses. So therefore, gradually this capacitor voltage will be reduces. Once the capacitor voltage is reduced this less than this value, right? In that case, it will stop working. So therefore, we need to regulate this one. So meaning is that we want to draw some real power from the source. We need to draw some real power from the source such that, so we will maintain the voltage across this capacitor, right? So that means this converter will be slightly lagging. So that means, this is grid side, and we have some inductor. If you model this one, we have some inductor, this inductor, and we have the inverter here. Okay. So now we need to draw some small amount of real power from here to here. So that means this one is slightly delayed, or we need to maintain some small phase shift between this converter, right? So this converter, so that the real power can be transferred from the grid to the inverter, right? So for that we need some extra controller. So simple controller. So we need to sense this voltage, right? So this VDC voltage reference value, and this is VDC actual value, and you have some PI controller will be there. So this PI controller will gives you the loss component, right? That is P loss. So accordingly, this angle will be adjusted. The angle between these two will be there. That will be adjusted. So where we need to add this one. So this is active power, right? So this active power. So we need to add in the compensating powers. So this is this is due to the loss component. So this loss is maintaining the DC voltage constant. So the overall controller will be something like this. So here the overall controller will be something like this, as we discussed. So here so similar to the rectifier units, or similar to the grid integration or anything, right? If you want to for higher levels or high voltage applications, the basic control is same. Only thing is that this inverter will vary. So depending on application, sometimes we use the 2-level inverter, 3-level inverter, or some cascade edge bridge inverter, some other modular multi-level inverters, and all. That will change, right? The basic control philosophy will remain same. So as we discussed, the first thing is that, so first we'll convert this into the Clark transformation, right? And also voltages, grid voltages also we need to convert this into Clark transformation. Sometimes what happens is that the grid voltages itself are not sinusoidal. Some small disturbances will be there in the grid voltages, right? So to tackle the disturbances, we normally use some phase local loops with some handling some disturbances like unbalances are there in the grid voltages, or some distortions are there in the grid voltages. So we need to use some proper phase local loop such that the disturbances can be rejected. Right. So we normally have some positive sequence voltage detector. So that is simple way to generate the positive voltages. So we have some disturbances are there, and from disturbances, so we can actually obtain this clean waveforms from the grid side. So first step is that we'll convert this into alpha beta reference frame, and we need to calculate the powers. So from that powers, we need to eliminate the, as we discussed, right, PDC component and PAC component. So by using some low pass filter or high pass filter, we can eliminate the AC component. For example, you are using a low pass filter, so that will eliminate the AC component. If you are using a high pass filter, so that can eliminate the DC component. Likewise. So generally, designing a low pass filter is somewhat simple when compared to the high pass filter. So therefore, we can use the low pass filter like this, and this entire thing will gives you the AC component, and this is the loss component, so that is obtained from the DC voltage controller. Right. So this will gives like this, and Q, it is a measured Q. If you want to invert this one, just we need to multiply -1. Right. So here the current reference are generated in the alpha beta reference frame, and this alpha beta reference frame. By using inverse current transformation, so we can generate the currents in the ABC reference frame, and we can use any PWM technique like sine PWM technique, or depending on this will change depending on the inverter. So we can use any kind of PWM method. Okay. So here the basic control, as we discussed, is remains same. If at all you are using some multi-level inverter, so where the change will come is that, so this will change and also this will change. These two things will change. The rest of the things will remain same only. So axing this loss component and the PWM technique, so that will be different. The remaining all things will become same only. Alright. So now we will see. So what are the additional things, or what the next step is that if you want to compensate the so if you want to compensate the unbalance, so which is very common nowadays because of this computer loads and all these things. So unbalance. So next we will discuss about the how to deal in case of unbalanced compensation. Right. So three-phase 4-way networks. So that is also used for unbalanced compensation. Three-phase 4-way based D-stat comes, so we can use it for unbalanced compensation. So first thing is that most of things are there. So unbalance is due to the uh, deviation in the sinusoidal waveforms, magnitudes, and as well as the phase angle deviation. Not only that one, even though it is balanced, if it is not sinusoidal, so we can expect a unbalanced. So let us assume this is the first case. So all are sinusoidal here. So all phase currents are sinusoidal. This is A phase current, B phase current, and C phase current. All are sinusoidal. If you are adding all these things, so you will get 0 here. So whereas here, so this is A phase, B phase, and C phase. So here balanced, but they are not sinusoidal. So here the currents are balanced, but they are not sinusoidal. If you are adding this one, so but you will consist of some neutral voltage, so neutral current. Right. So what meaning is that if you want to make the neutral current 0, the source currents, all three-phase currents must be sinusoidal and must be balanced. So then only the current will become 0. If it is a small deviation in the magnitudes, phase angle, right, or if it is not sinusoidal, that also leads to the neutral current. So this is an example. So here unbalance here, and this is the amount of neutral current. And you can see that neutral current consists of all kind of harmonics like third order, fifth order, seventh order, all kind of harmonics so that are present. So to deal with neutral currents, this neutral current is as it is problematic, especially in case of the data centers and all. The neutral current size, it will carry more current compared to the phase currents. In case if it is completely with computer kind of loads or some data centers or server kind of loads, right? In that case, the neutral having more current when compared to the phase. So therefore, they normally increase the size of the neutral wire. In usually, so if it is 1.6 times or 1.7 times more size the required for neutral compared to the phase conductor. Right? So neutral current can overload the distribution feeders, so they will induce some common mode noise. So flat topping of the voltage waveform, so wiring failure. Some of the temporary measures is the oversizing the neutral current and derating the transformer, and also separate neutral conductors, like separate neutral conductors for different applications. So commonly used solution for DSTATCOM solution for this neutral current is that, so one is the three-phase H-bridge topologies, and using four-leg topology and this capacitor midpoint topology. Okay. So this requires three transformers and 12 switches. Therefore, this is not preferred. These two solutions are promising. One is the four-leg topology and the capacitor midpoint topology. So here in case of four-leg topology, so we have additional leg is there. So additional leg is to control the neutral current. So whereas in case of a capacitor midpoint, so instead of using an additional leg, the capacitor is splitted here. The capacitor is made into two parts. We have only one capacitor, right? This capacitor now we made it two. So we have the point, so where we connect the neutral current here. So one is the four-leg topology and another one is the capacitor midpoint topology. In case of four-leg topology, the control is simple. So these three will be controlled separately, right? This one is connected to neutral. So these three is connected separately. This is the neutral leg. So this neutral leg is controlled separately. The control for this one is simple. You know, right? We need to inject the neutral current in the reverse direction. So what we can do is that we will measure the currents. This is ILA, ILB, and ILC. We will measure, right? And we will add all these things, and we can generate the neutral current. Right? So we need to operate this one such that we will get the or such that we will inject in the reverse direction, right? So therefore this will be the reference for this third leg, and we will operate the fourth leg, and we will operate this fourth leg in a current control manner such that we can easily control this one, right? So this is how it is controlled, fourth leg, and we will add all this, so that gives you the neutral current. And this is the neutral current of this one, and we'll compare this one, and we have some simple PI controller, and this is compared with some carrier, right? And based on that, it will generate the firing signal for this switch and as well as this switch. It is simple. So this is current control method. So this one, what we seen here is the triangle carrier, current control method. Similarly, we can also use the hysteresis current control method. So in case of split capacitor, so we need to, in the control itself, one thing we need to understand in case of zero sequence voltage or the neutral current present, right? In case if the neutral current is present, under this case, so this is not zero. It is zero. It is zero only when it is balanced. If it is unbalanced, so you will get some zero sequence power. You will get some zero sequence power. So this power curve thing, so we need to include in the controller, right? Somehow, so we need to include this power coefficient as well, right? This matrix will be elongated, and you will get this third element as well. You will get this third element for the neutral current compensation. Right? Okay. So this is how it is compensated in case of this topologist, right? But there are drawbacks here. So when you have split capacitor, right? So when you have split capacitor, so there is always a problem that this capacitor will deviate. This capacitor voltages will be deviated. So we can use some advanced PWM methods like space vector modulation technique or the model predictive control. So to minimize this deviation, and also we can use some external circuits. Right. So we can also use some external circuits to reduce this deviation. Yeah. So if you have, this is one capacitor, right? It's not an issue. If your multiple capacitors are there like this, you have two capacitors are there, and this point it is connecting the neutral. So we can slightly we can add some more elements, something like this. We can add one switch here, and we have something like this. We have some inductor, and we have another switch here. Right. Right. So this is the remaining part of the inverter. We have one switch here, right, and we have another switch. Right. So this is A phase, B phase, and C phase. This is the point where you connected the neutral. And this one is additional circuits, are also known as this auxiliary circuits that we connected. Right. This is the auxiliary circuit E connected here. So this will act as a two-quadrant chopper circuit. Like somehow the operation is fairly simple. Let us assume that this is excess charge. Let us assume you need to maintain 700 volts as here. This supposed to be, ideally this supposed to be 350 volts, and this is also supposed to be 350 volts ideally. Somehow this is excess charge. Let us assume this is become 360 volts, and this becomes just 340 volts. Okay. So what happens is that this is excess charge, right? So now what we'll do is that we'll turn on this switch, right? So we will turn on this switch. So we'll turn on this switch, right? And if you close this switch, what happens is that, so this capacitor and inductor, whatever this one is there, right? The current is transferred like this, and it will charge this inductor, or it will store some energy in the inductor. So how long we need to store until this become, what happens, this capacitor will be discharging, slowly its voltage will be reduced. So once this voltage is changed to 350 volts, if this voltage is 350 volts, so now this we will open this switch, right? So we'll charge this, or we'll discharge this capacitor, and we'll transfer the energy to the inductor. So we'll discharge this capacitor, and we will energize this inductor, or will transfer this energy to the inductor. And how long it will be? Until its value reaches 350 volts, right? And this is the point where we open the switch. So now it consists of some charge or some stored energy in this direction. So now what we'll do that, right? We will turn on this switch. We'll turn on this switch. So here the inductor current will not change its direction, right? So therefore it will charge this capacitor. It will charge this capacitor. So once again it touches this 350, and it will recover, capacitor voltage is recovered. So again, if it touches 350 volts, and this is the point, so where this switch will be off. So this way, whatever, that means if the one capacitor is excess charged, if upper capacitor is excess charge, this charge is transferred to the inductor, and again inductor to the bottom capacitor. Similarly, upper capacitor, again same thing. If it is, for example, if this upper capacitor is charged to 360 volts, so let us assume this is charged to 360 volts, and we turn on the switch, right? And now this capacitor, it will charge in inductor in this direction. So once it reaches 350 volts, and this is the point, we will turn off this switch, and we will turn on this switch again, and again this inductor current will flow like this, and it will charge the upper capacitor. It will charge the upper capacitor. Again, this upper capacitor voltage is recovered, and it is become 350 volts again, and this will turn off both switches. So this is how we can maintain the charge, or we will balance the capacitor voltage by using some external circuits. This same thing it is shown here. We have this one. So this is the point. This one is the point where it is neutral current is connected, neutral wire, so which is connected here, right? And we have this one, the switch arrangement. So this entire setup. So which one is known as the two-quadrant chopper, the two-quadrant DC-DC converter. So here, the excess charge in one capacitor is transferred to the inductor. From this inductor, it is connected to the other capacitor. This is how it will work. So in case of three-level inverters, right? So three-level inverter, the same problem arises, right? Three-level inverter also, the same problem arises. And in case of three-level inverter, even it is a neutral current is connected or not connected, but it is arises, right? For example, you are using a three-level inverter here. So two-level inverter, you have only one capacitor, whether it's a three-phase three-wire network or three-phase four-wire network. You have a three-phase three-wire network, so you have only one capacitor. In case of three-phase four-wire network, you have two capacitors in two-level inverter. But if you are using a three-phase three-level, if you are replacing with a diode clamped multi-level inverter or this new the T-type inverter, in three-phase three-wire itself, three-phase three-wire itself, you have two capacitors, right? You have two capacitor here itself, right? And the rest of the things is some T-type inverter or some diode clamp inverter, right? So to avoid this one, or again voltage balancing, everything will comes now. Let us assume this is a diode clamp T-type or diode clamp T-type. So both of the control strategy is same. So your two split capacitors are there. This is one capacitor and this is another capacitor. The idea same thing. You connected one switch here, you connected one switch here, and this is how the charge is balanced from one circuit to the other circuit, other one capacitor to the other capacitor. The same thing can be done for if your four capacitors are there or some four capacitors are there. So similar way you can balance the voltages. This is in case of five levels. Right? If you have four capacitors, this is 1, 2, 3, 4. Right? So now we connected. Right, this is slightly complex. So this entire thing is for the voltage balancing. This entire thing is for voltage balancing. Right. So here you see that, right? So this is one chopper circuit, and this is another chopper circuit for the bottom two capacitors. So here, if this is excess charged, so this charge is transferred to this inductor. So from this inductor to the capacitor. Similarly, this is from this capacitor to the inductor. Inductor to capacitor, and capacitor to inductor, and inductor to the capacitor. Right. So if you observe that, why we need these two switches in series, right? Actually, this is one switch here, but we represented as a two switches because thing is that, right, when you are connecting the two switches here or somewhere here also, if you are connecting the two switches, right, one important thing is that, so you have to make sure that this one is supposed to block the entire DC link voltage, right? The switch is supposed to block the entire DC link. For example, this is off, right? So there is a chance that it's supposed to block the more voltage when compared. That means this switch is supposed to block this inductor voltage and as well as the capacitor voltage, right? So that extra voltage is supposed to block. So whereas in this case, for example, this top switch is on, right? This switch is off, right? So that means it's supposed to block this capacitor voltage and as well as this capacitor voltage. So that's why this switch is supposed to block double the voltage of this normal switch, right? There is the reason we connected two switches in series. Similarly, here also two switches in series. So it is just a single switch, just we are representing that this is not a single switch. So we need to consider double the capacity. Let us say if we select 1.2 kV device and this entire thing supposed to be 2.4 kV device, or else two 1.2 kV devices, single 2.4 kV device or two 1.2 kV devices you're supposed to keep. Okay. So that's why these are some drawbacks here. For example, you need to connect 8 switches, right? And also we have some inductor and inductors also included, and additional control circuit is there just to handle the unbalance. Right? So in case of cascade edge bridge, so in case of cascade edge bridge kind of thing, let us assume this is operate. This is operate. This entire thing is used as inverter. Right? Cascade edge bridge inverter. This is more common for a D-STATCOM or STATCOM applications because to withstand higher voltage rating, so we need to employ this cascade edge bridge inverters. Okay. So we need to employ this cascade edge bridge inverters for high voltage applications. So let us assume that you are connected to a 11 kV grid, right? So let us assume that you are connected to a 11 kV grid. Here the design is simple, right? So here this 11 kV is the line to line voltage. So that means phase voltage will be 11 kV by root 3. 11 kV divided by root 3. That is your phase voltage. Right? So that means the voltage between, or you need to suppose to provide a voltage between from here to here, right? If you measure, it's supposed to withstand from here to here, it's supposed to withstand this much voltage only, right? So this much voltage only. So here the design is simple as we discussed. Normal, there is some small thumb rule here. So if you want, if you give some 1000 volts on the DC side, right, you will get a 625 volts RMS value on the AC side. If you are giving 1000 volts on the DC side, you usually get a 625 volts on the AC side. 1000 volts DC. So here also, if you are giving 1000 volts, here you will get 625 volts AC RMS. Right? Right. So here, how many bridges you want to connect in cascade? So your voltage is 11 kV divided by root 3 divided by. So let us assume that 6000 volts each DC bus here is DC voltage you are selected. So that is 625. Right. So 11 kV by root 3, 625. So this many number of bridges it's supposed to connect. If you calculate or if you transform this one, it is something like this: 11 kV divided by 1.7. So this will be roughly 6,350, right? Divided by 625. So it is roughly 10, right? Roughly 10. If you're keeping something, right, some factor of safety, or if you slightly modify that means 10 devices or 11 devices you're supposed to connect. So 10 or 11 devices is supposed to connect to directly design a 11 kV D-STATCOM. 11 kV D-STATCOM. So that means 10 H bridges you need to connect in cascade per phase. 10 or 11 H bridges you need to connect in cascade, right? And another thing is that 10 or 11 H bridges in cascade. And another thing is that each DC voltage you're supposed to maintain at 1000 volts, right? If you don't want this one 10, right, you can always change it, right? You can always change it. Maybe you can increase this DC link voltage. If you're increasing this DC link voltage or this DC voltage, so that will reduce the number of H bridges in cascade. If you are further shorten, if you require only 500 volts you are using, right, in that case maybe you need to connect 20 or 21 devices or 20 or 21 H bridges in cascade. And then thing is that, so you need to maintain these edge bridges in case whatever these bridges there, right? You need to maintain the voltage across these edge bridges constant. So here in reality, so this will only not DC source, these are just capacitors. In case of this STATCOM, so these are just capacitors only. So these capacitors, you need to maintain its voltage. So to maintain the voltage, that's a slightly complex thing. So there are different methods are there. Let's assume that we are using a 5 H bridges in cascade, 5 H bridges in cascade, right? So that means you have 15 H bridges for three phase. It is 5 into 3, right? So that will form a 11-level inverter. That will form a 11-level inverter, right? So here thing is that we need to balance all the 15 capacitors, right? We need to balance all these 15 capacitors. The first thing is that first thing is that there are two things are there. One is the cluster voltage balancing and the individual voltage balancing. So that means this DC link and this DC link. So this entire thing acts as a cluster or one phase leg. So this entire thing is acts as a one phase leg. This entire thing is acts as one phase leg. So this is known as the cluster voltage balancing. So here we will measure these two capacitor voltages, right? Let's assume this capacitor voltage is VC1 and this is VC2. So we will add this VC1 plus VC2 and we'll compare with the reference value, and we have one PI controller here. This is for A phase. Similarly, do this for B phase and C phase. We'll do this for B phase and C phase. So this is known as the cluster voltage balancing. So whereas individual voltage balancing, each capacitor voltages, right, like each capacitor voltage is VC1, right? Or this one is compared with the reference, right? And we have one PI controller will be there. All these things do it for the all capacitors. Similarly, we have VC2, so that is compared with the reference. Right? We have VPI controller, you'll get some parameter. So depending on that, so we need to use or we need to properly handle these outputs of the PI controllers. Right? So that's why it is cluster voltage balancing. So they're controlling this entire phase leg at a time, and individual voltage balancing. Each one we have one PI controller, like A phase all one individual PI controllers, B phase all one individual PI controllers, likewise. See, if you see this one, right? So this one is the cluster voltage balancing. You are measuring all the voltages. Some just low pass filter. Generally, a low pass filter is there required for this capacitor voltages. And we have added all these things, and we are comparing with a common reference. This is for A phase, B phase, and C phase, and we have obtained some loss component. Generally, this loss component, depending on what kind of PWM method you are incorporate, this loss component may be a power, or sometimes it may be a voltage form. If you are using a voltage control PWM methods, it is in the form of voltage. Right. So this is individual voltage control individual balancing for all the 15 voltages. This is A phase voltages, B phase voltages, and C phase voltages. We are comparing with a reference value, and these are individual PA controllers. And this entire thing we are clubbed together. This is one loss component. The total loss component will be a cluster voltage balancing loss plus individual voltage balancing loss. We will add these things. This is the total P loss that is obtained. So this is the total loss component, so that we obtained from this. So this way, so you can use the you can control the cascade HPs converters or some. Right. And another thing is that the tuning of this one PI controllers is sometimes usually simple. We are using a PWM method like the phase shift PWM technique or something, right? So we can easily tune the capacitor voltages. If you have properly tuned the capacitor voltages, it will be I think my results are there. So these are the capacitor voltages. Like this is for the 11 kV system I used, right? So this is voltage here, and this is the uh, source current. I connected a D-STATCOM at some 0.04 seconds. These are the load currents, and this is the D-STATCOM currents, and these are the capacitor voltages, right? You can see these are the capacitor voltages in a phase. Okay? You have 5 capacitor voltages, 1, 2, 3, 4, 5 here, and all the capacitors are maintained at 2.5, 2500 volts, 2500 volts. I used only 5 H bridges per phase, 5 H bridges per phase. You can actually design this one something like this. Right. You can use the H bridges like 2 H bridges. So this will be the DC link voltage. But if you are using 11 H bridges, this will be the each cell voltage, and this will be minimum voltage, maximum voltage. You can put some imposes on this one design principles, right? You'll get the 23 levels here and all these things, number of levels of the phase voltage, and this is the THD here, right? So I selected this one, right? Okay, somewhere between 2500 volts, so we can maintain the capacitor voltages. And I got a THD for this design, so maybe you will get some 6.83% THD also. Uh, we will stop here. If you have any questions, please ask.
If you have any questions, you can post in the chat box.
Yeah, please. Yeah, please. Yeah, please. Go ahead.
Srini, can we use CSI instead of VSI?
Yes, we can use CSI instead of PSI, but if you are using CSI, again, you need to use a large inductor. So maintaining the current in the large inductor is okay up to 5 amperes or to 6 or 10 amperes range, but larger systems, it is very lossy.
Sir, is there any time delay need to be considered for measuring the signal and arriving the transformations and finally controlling the inverter? So the harmonic, the every millisecond it need to compensated.
No, these signals are very fast, right? These are in the gigahertz range, right? These transmitted signals or whatever the signals that we are obtained from the different measurements, right? They're very fast. Okay. Uh, that uh, that that delay, I think we don't need to consider unless we
Actually,
are.
that voltage, yes, sir, voltage and current sampling from the CT and PTs. This thing need to convert it into digitalize, and then this transformation should be take place, and later that control signal should be given to the inverters. So is there any kind of adjustment is there, or as you told straight away the signal will be very fast?
Straight away we can use that. Now nowadays we are using optical cables and all. No? We no need to worry about that. Even though the delay is very small only, it is in the order of 1 or 2 microseconds only. That does not give any performance changes. If unless
Okay,
your
sir.
application is something like that, something like the what we say, some pulse power generator or something. If your application is that, no, in that case you need to worry about that. On these
Yes,
kind
sir.
of applications, we no need to worry. Whatever the output that is obtained from the uh, sensors,
Normally employing the D stat comes in the normally employing the D stat comes in the distribution transformers of any discoms. So it can straight away implement it,
yeah,
no?
we can
The
straight away
known,
use some optical cables. No, that is very fast.
yes, sir.
Even one
Yes,
or
sir.
two microsecond delay is there. No, that will not impact the performance that much.
Because that compensation should be exactly done in the same instant itself, no?
Yeah, exactly.
There should not be any time delay. Then, if that there is a time delay means, then that injecting the signal again, it will create a harmonics, another kind of harmonics,
No,
isn't
the
it, sir?
point is that no, the delay maximum delay is in the order of less than 1 microsecond or something. No, even that small
Oh,
delay only, that
microsecond.
will not
Oh,
your
microsecond. In order of microsecond only, the
it will
entire
not
thing will be
impact the
happen.
performance much.
Okay, sir. Thank you. Thank you, sir.
Sir, good afternoon, sir.
Yeah, please.
Sir, for neutral current compensation, there is a two topologies are using. One is split capacitor 3-leg topology, and another one is 4-leg.
Yeah.
So, which one is better, sir, for neutral current compensation?
Depending on what magnitude of current you are compensating, right? As we
Okay.
discussed, in case of neutral current compensation by using a split capacitor, right? We discussed the drawback, right? The capacitor unbalance is there among the individual things, right? If that, one second, I will show you the figure. So this is the figure we are talking, right? So this four
Yes.
leg is everyone has their own drawbacks and merits. The capacitor midpoint, the biggest drawback is the unbalance among the capacitors, right? If the current, if you are injecting large current among into the capacitor split point, right? So that obviously leads to the large deviation in the capacitor voltages. So maybe the point is that if you are using for a low current levels or low voltage system, maybe the split capacitor or capacitor midpoint is a good solution. But for all high power cases and all, so four leg gives you the best performance.
So, for example, if a large neutral current is there, then 4-leg topology is suitable for it can
Yeah,
be withstand.
large current. If you that is four leg is the best option.
Then, what is the purpose of chopper, sir? For sometimes you are using 3-leg split capacitor with chopper circuit, no?
Yeah, chopper circuit will eliminate. It will balance the capacitor voltages.
So that is case of high neutral currents.
Not high or no low neutral currents. Generally, it depends on as we discussed it. So if you are directly injecting, you are making two. You are directly injecting current into the neutral point of the the split point of the capacitors. There is a chance that the capacitor voltages always deviate. Right?
Yes, sir.
So to reduce the deviation, so we are using the chopper circuit. In case of two-level inverters, that may not be an advantage, but in case of three-level inverter, that is necessary. For all three-level inverters, I on that or for three-level neutral point clamped or T-type inverter you are using, so you must have a, or you, most probably you need to balance the capacitor voltages. So for that, the chopper circuit is necessary. Right. So again, if you are using a two-level inverter and you are using a chopper circuit, instead of that, you can directly go for a four-leg, right? So four-leg, you have only one capacitor.
Yes, sir.
Any more questions?
Any questions? See, on yes, sir.
Yes.
On what factors the power rating of the district will depend, sir?
The main thing is that two things. Normally, these statcoms are rated in not in a power rating KVA rating. Usually, it is rated in KVAR rating. All these FACTS devices like D-STATCOM, STATCOM, they have KVAR rating. So how much load consists of how much amount of maximum reactor power that exists. So depending on that, they usually design the rating. So current rating depends on the reactor power rating. Only.
It won't be considered any harmonic current also, right, sir?
Generally, the compared to the harmonic current, the reactive current will be much higher. No? So that's why reactive power current itself is sufficient. So how much reactive power? What the first thing is that we need to thoroughly do the harmonic analysis of the load profile, harmonic analysis and the reactive power currents inside the load profile. So based on that, we will select the rating. So majority of things or the majority of the current is from the reactive power only. So therefore, reactive power current measurements is usually sufficient for this.
Okay, then, is there any questions are there? Sir, can you stop sharing the screen, sir?
Sir, excuse me, sir.
Yeah, please.
Sir, actually, I want to uh, get that reference paper for my DC bus voltage control for multi-level inverter. Can you share it, sir?
I will share this one. Which exact inverter you are using?
Multi-level inverters.
No, no. What multi-level inverter inside?
During last session, sir.
During last session, you had a cascaded H bridge, sir.
I will share that one.
Oh, thank you, sir.
Yeah, I think like yeah.